Let's take a look at section 14.1, iterated integrals and area in the plane. Now in the previous chapter, we looked at differentiation of a function of multiple variables. And we saw that there is no single differentiation anymore. We look at derivatives with respect to a particular direction. If you're taking a derivative with respect to the x-axis, with respect to the y-axis, or with respect to the direction of some vector, you have the partial with respect to x, the partial with respect to y, or some combination thereof, which we call the directional derivative. Well, what about integration? So that's what we're looking at here. If we're looking at section 14.1, let's go ahead and talk about integration. Now, if you have a function of multiple variables, let's say, for example, a function of x and y, then taking a derivative doesn't make sense. You have to be more specific. You have a derivative with respect to x, and that's different from a derivative with respect to y. We call those partial derivatives. Right? Now, if we're going to talk about integration, it seems apparent that we are going to have to make some distinction as well. So let's go ahead and see what that looks like. When we integrate a function, there's going to be a difference between integration with respect to x and integration with respect to y. The way we are going to be able to tell is this differential is going to indicate our variable of integration. So if we're integrating that same function, we're going to get two different integrations depending on which variable we consider. In a bit, this is going to take on a physical meaning. But for right now, let's just see what it looks like computationally. So here, this would be your variable of integration. Just like with a partial derivative, a convenient way to do this is to assume one variable is still variable. All other variables are going to be considered constants for the duration of that problem. So take, for example, the following function. Let's say f of x equals 2x plus y squared. Now, to integrate, that should be f of x comma y. To integrate, the answer will depend on which is our variable of integration. So here, let's do it both ways. Let's say I'm going to integrate the function 2x plus y squared, and let me do it with respect to x. And then separately, let me go ahead and do it with respect to y. So integral of 2x plus y squared. Notice it's the same function, but if we're integrating with respect to x, that means y is a constant. Well, okay, x is a variable, and the antiderivative of 2x will be x squared. This is a constant, and the antiderivative of a constant is a constant times the variable of integration. For example, if I was taking the integral of 5, I would get 5x. The integral of 12 would be 12x. So here the integral of y squared will be y squared x. Just like that. Plus a constant of integration. This constant of integration will be will act a little funny, as we'll see in some applications later. But again, for right now, we're just seeing what it does computationally. In application, we're going to have to be a little bit more careful with this. Over here, we can do something similar. We're taking an integral with respect to y, which means this is a constant. And if I take the integral with respect to a constant, well, it's that constant times the variable of integration. Plus, if I take the integral of y squared with respect to y, that's going to be y to the third over 3. Plus, again, our constant of integration. Once you have your constants of integration, we want to make note of something. This is a constant. Well, yeah, but this integral is with respect to x, which means this constant might possess the variable y. Because after all, with respect to x, y is a constant. So when we say plus c plus a constant, it might be a normal constant like 12 or -5, but it might also be a constant with respect to this variable. So this might be a number, or it might be a multiple of y, or some combination thereof. This might be 2y plus 5. It doesn't have to be a constant It just has to be a constant with respect to this. So the way we write this is a constant. It's a constant function with respect to x, but it may still possess y. So here this is like saying a function of y. It doesn't possess x anymore, only y, since that's constant with respect to this integration. Likewise over here, this doesn't have to be a constant in the traditional sense. It just has to be constant with respect to y, which means it may be a function of x, just like that. Note that boundaries of integration may still be a thing. So here, let's go ahead and integrate from, let's see. Let's go from x to the third up to the square root of x. And our function will be x squared plus 3y squared dy. Okay? So notice that you have boundaries of integration. And you say, whoa, hold on. Those boundaries are variables. Aren't they supposed to be constants? You know, from 0 to 5 or from 2 to 20? Well, they are constants. With respect to y, those are constants. So just like over here, it doesn't have to be a constant. It just has to be a constant with respect to that. Same thing here. All right, so just like we've seen in previous examples in previous chapters, when you integrate, you're just taking the antiderivative, you're plugging in the endpoints, and you're subtracting. The difference now is that you're integrating with respect to this variable, as opposed to just, there's only one variable, and I don't have to worry about that. So let's see here. The antiderivative of this would be, that's a constant, and the antiderivative of a constant is the constant times y, plus this is a antiderivative of 3y squared, and since that possesses y, well then that is a regular variable, so here we would treat this as a regular antiderivative. Y to the third over 3. And now, here I would put a constant of integration, but since we're looking at a definite integral here, we're going to go ahead and evaluate from our lower bound to our upper bound. Notice if you put your constant of integration, even if it's a constant function, by substituting in these values, you'd end up subtracting that expression away anyway, and just like in Cal 1, the constant would disappear. So for a definite integral, and here this is as definite as these are going to get, because after all, these are constants with respect to y, we don't need that extra constant. So here we go. Note that you're plugging in for y, so that's going to be x squared times square root of x plus square root of x to the third power over 3. Remember, these are the values of y. Now, separately, let me plug in x to the third. So I get x squared times y, which is now x to the third, plus x to the third over 3. And then those will be subtracted. All right, so this will give me, let's see, that's, there's not much we can do here. We can write this as x squared square root of x plus 1/3, square root of x to the third is x root x minus, these can be multiplied. That'll give me x to the 5th power. And here that'll be x to the third. Don't forget to distribute your minus there. And that's going to give you 1/3 x to the 3 to the power 3 would give me power 9. And that's it. That's about as far as we could take that. I suppose there are ways you might want to try to factor out common factors or things like that. Let's not worry about that. This will suffice right here. Let's take a look now at a different example. Let's say we're going to go ahead and integrate from e to the y up to y natural log of x over x dx. All right, so, and pause the video here for a moment. Give this a try. And once you have reached an answer, go ahead and unpause and we'll go through it together. All right, well, you'll notice that x is the variable of integration, which means y is a constant. Here, to help make things a little bit easier on myself, since it is hard to keep track sometimes, I'm going to write this way. I'm going to write this as y times natural log of x over x. Obviously, those mean the same thing, but now by putting a little distance here, I visually remind myself, hey, that's a constant. Don't integrate that one, just with respect to x. All right, well, now look, the natural log of x over x. Oh, well, integrating with respect to x, that one's nice. Just over here, a little scratch work. The natural log of x over x, if I take its antiderivative, I can write this with a u substitution. U is equal to the natural log of x, which means du is 1 over x dx. So this would become the integral of, well, the natural log of x is just u now, and that dx over x, that's just your du. So this would be just u squared over 2, plus some constant of integration. So over here, if I'm going to take the antiderivative of this, remember that's a constant. So I don't have to worry about that one. Here, this is going to be y times u squared. Well, actually I should put that back in terms of x, shouldn't I? So this would become natural log of x squared over 2 plus our constant of integration. So here this would be y times the natural log squared of x over 2. We're not going to worry about that plus c here because here we're looking for a definite integral, and that constant would go away on us anyway. So now we can go ahead and substitute our endpoints, subtract, and we're done. So that would give us, now remember, you're substituting these in for x. That's your variable of integration. In some cases, some people actually prefer to write that. They'll write x equals this and x equals that to help keep things straight for them. So here we can write this as y, natural log squared of y over 2. And then here, we're taking our lower boundary, which is y, natural log squared of e to the y over 2, and we're subtracting. Note there isn't really anything you can do to simplify that part, but here that simplifies because the natural log of e to the y is just y. Don't forget the whole thing's being squared though. So here that's going to give you y, natural log of y squared, and I'm going to go ahead and write this way, over 2, minus, here I can write this as y, natural log of e to the y just gives me y, but don't forget that whole thing's being squared. So that's y squared over 2. And of course that simplifies down a little bit more to give me y, natural log of y, quantity squared, over 2, minus y to the third over 2. Now, the next thing we're going to look at is when we looked at derivatives, we saw the possibility of taking higher order derivatives by taking the second derivative, the third derivative, the fourth derivative. But when we take those higher order derivatives, we don't have to take them with respect to the same variable. We can have mixed partials. We can take the partial with respect to x, followed by the partial with respect to y. Integration has something similar. This is called an iterated integral. And an iterated integral is what happens when you take an integral of an integral. So let's take an example. Let's consider the integral from 1 up to 4 of the integral of 1 up to the square root of x of 2y times e to the minus x dy dx. Right. Now the way this is written, you should consider this as a chain of events. Starting from the inside and working your way out, you should take an integral, and then once you resolve this and get a result, you take the next integral. So this one would go first. In later sections, we'll have iterated integration of more than two variables. So again, it would work from the inside, and then you would do this one. And then, if there were any more integrals, you'd continue on to those. So let's write down integral from 1 to 4. Over here, that's dx. And let me leave myself plenty of room to work in here, because I'm resolving that first integral first. All right, well, if I'm integrating with respect to y, that means x, or any term or factor of x, is considered a constant. So here, that's just a constant number. So here, that's 2y e to the minus x. That's really just a constant times y. Oh, and that's nice, because if I take the integral of a constant times another constant times y dy, well then, I'm just going to take that y raised to the second and divide by 2, and that constant's not really going to bother me. So here I could write this as 2e to the minus x times y squared over 2. And since those 2's cancel out, I'm left with e to the minus x times y squared. Okay, so here I'm going to get e to the minus x times y squared. And of course, we're evaluating that from an upper bound to a lower bound, from square root of x as the upper bound and 1 as the lower bound. Now remember, here you integrated with respect to y first. So at this step, we're going to go ahead and substitute these in for y. I'm still going to write the integral from 1 to 4 because I haven't done that yet. I haven't resolved that integral. I'm still working in here. And now the stuff in here is going to be, well, my y is going to be replaced by the square root of x. So that's going to be e to the minus x, the square root of x squared. Well, it just gives me x. Minus, here I have e to the minus x times 1 squared. Well, that's just the number 1. And all of that is my antiderivative with respect to y. So now, rather my integral with respect to y. So now I can resolve this second one. Notice now everything is with respect to x, which means now I can integrate. This is now just a standard integral with respect to x. So now I'm back in Cal 1 or Cal 2. Here, let me take the antiderivative of this one. It looks like I need integration by parts. After all, that's a product. So let's go ahead and do that right over here. If I take the integral of x e to the minus x dx, that's going to be, I'm just worried about that part, that's going to be integration by parts. If I take x and call it my u, then du is equal to dx. Well then, if I take dv to be the remainder of this, to be e to the minus x dx, the antiderivative, the v, is just going to be minus e to the minus x, plus a constant, but we're not going to worry about that for this, because here we're looking for a definite integral. The constant won't matter. Okay, so the integral of this is going to be, take your u times your v. Okay, so that's negative x e to the minus x. That's my u times my v, minus the integral of v times du. Well, v's got a negative, so negative of a negative makes that a positive. And that's going to be e to the minus x dx. All right? That was minus, but now minus of a minus makes that a plus. And now I can integrate that part because that's just minus x e to the minus x. The antiderivative of e to the minus x dx would be minus e to the minus x. Plus a constant, but again, we're about to substitute in some values, so for once we don't worry about that extra constant. So here, that antiderivative is going to be minus x e to the minus x minus e to the minus x. And now right here, don't forget, I only took the antiderivative of this first part. I now need the antiderivative of this second part. But the antiderivative of minus e to the minus x, well, double negative will make that a plus. So that'll be positive e to the minus x. and that'll be evaluated from 1 up to 4. Those are our boundaries. Notice here these two subtract away, so I have a much simpler expression of minus x e to the minus x evaluated from 1 up to 4, which is a little bit simpler to plug into. Finally, let's go ahead and plug in the numbers 4, the number 1, and subtract. So let's see, we get negative 4 e to the minus 4. And then when we plug in 1, we get negative 1 e to the minus 1. And then those two are being subtracted from each other. And it doesn't look like there's much we can do to simplify. Here we can write this as minus 4 e to the minus 4. Double negative makes that a plus, so that's plus e to the minus 1. We could factor out e to the minus 4 as a common factor there, but that'll suffice to be our final answer. Okay. So iterated integrals are just integrals repeated. The application for this leads us to the next, or an application of this leads us to the next section, to the next part of our section. Whoa, what was that? My screen flickered there for a second. Anyway, so we have a problem that we've seen all the way back in Cal 1, and that was the problem of the area between two curves. Okay, the area between two curves, and let's go ahead and draw that out here. Let's say I have the xy coordinate axis, and I have two functions. Y is a function of x for now, and here we have y is another function of x. And here, this is y equals to a function of x, and here y is also equal to a function of x. Now, normally we would use f of x, but I'm going to use g of x because I'm going to reserve f of x for something in just a moment. Here, these are two different functions, so I will call this one a g1, and I will call this one g2, just to be able to distinguish them later. So now, if I want to find the area between those, here, let's go ahead and make these perfectly flat, just like this. Incidentally, this is called a vertically simple region. This will come in, this will be necessary later, but for now, let's just go ahead and label this. This is a vertically simple region. And the reason it's vertically simple is because the vertical sides are nice and flat. In other words, here, these could be described as a constant. This could be described as x is equal to 5, and this could be x is equal to 12. All right? So here that is because the sides, not the top or the bottom, but the sides can be described by a constant. Okay, so if you think back to Cal 1, the way this works is you just integrate. And in fact, we have a specific integral. It's going to be the integral from a up to b. And in fact, I should probably label those. That's the integral from a up to b of the upper bound, that's g of square, that's g2 of x, minus the lower bound, g1 of x. All right, so that's something that you take a section or two in Cal 1 to go through and prove and confirm and do examples of. But for now, this is, but by now, this is something nice and familiar to us. What we want to do, though, here is we want to notice that this g2 of x minus g1 of x could be expressed in a different, albeit somewhat strange-looking way. Look at just this part. g2 of x minus g1 of x. Well, that's a function of x, and that's a function of x, and they're being subtracted. But that's what you get when you take an integral. Right? That's what you take an integral with respect to x. If you integrate with respect to x, you end up with two functions, which you can then subtract. Actually, I take that back, with respect to y. If I integrate with respect to x, I get two functions of y, which I subtract. Over here, if I integrate with respect to y, I end up with two functions of x which I can subtract. So notice, whichever variable I integrate with respect to, I'm going to get two functions of the opposite variable that are being subtracted. So right here, I could write this as the integral from, well, that's going to be the thing I'm subtracting, so that would be my lower bound, g1. That's the thing I'm subtracting from, so that would be my upper bound, like this, dy. If you take a moment, the integral of dy is just y. And if I'm evaluating it at these two endpoints, that would be, I would substitute in that for y. Separately, I would substitute that in for y, and then I would subtract. Well, that would be g2 minus g1. That's exactly that. So this expression here can be written as an iterated integral from a to b, and then from g1 up to g2, dy dx. Just like that. This can be generalized in the following statement. So let's consider the area of a region in a plane. So we're going to start off with the region R. So if that region R is vertically simple, which again just means that the sides can be represented by constants, let R be a vertically simple region where x is bound between a and b, those are just constants, and y is bound by some lower function which we'll call g1 and some upper function which we're calling g2, where g1 and g2 are continuous from a to b in that interval. If that's the case, then the area of this region R can be described as the iterated integral, the integral from a to b of the integral of g1 to g2 dy dx. Now, if this is not vertically simple, we have the possibility of something being horizontally simple. Here's a related expression. It looks very much the same, except you'll note that we've flipped the roles of what's constant and what's not. Here, let R, our region, be horizontally simple, meaning these horizontal lines, this top and this bottom, can be represented by constants. So let R be a horizontally simple region where y is going from a low of c up to a high of d, and here we don't use a and b just to keep them from mixing here, and x is bound between h1 on the left and h2 on the right, where h1 and h2 are continuous from the bottom to the top, nice continuous lines. Then the area of R is given by the iterated integral. Now, before we started with the integral with respect to x. Now we're starting with the integral with respect to y. The outer integral, the one on the outside, is always given by the one that has constant boundaries. So the one on the inside would be the remaining one. Notice, because now that's been flipped, notice that our order of integration has been flipped. Before we would say, okay, start with an integral with respect to y, and then an integral with respect to x. Now we're saying start with an integral with respect to x, and then the integral with respect to y. And here's a quick illustration of what that would look like. Note we don't really need the graphs for any of these. All of this can be done strictly algebraically, but just for a quick visual, what we're doing is we're looking for the area in between those two curves, in between y equals x to the 3 halves and y equals to 2x. Ignore the real part here. My program allows me to deal with imaginary components. We're not going to worry about that, just the real parts. So we're looking for that area in there. Okay, so let's go ahead and write this out. We saw our graph already. Like I said, it doesn't really matter what the graph looks like. Here we're going to do this entirely based off of the computation, based off of this, but it's nice to have an image before we get started. So in any event, what we're going to do is we're going to look for the find the area of the region bound by y equals to, what did I say here a moment ago? X to the 3 halves and y equals 2x. which we saw just a moment ago in the illustration. Note that we won't need any of this stuff in the illustration. All right, so first of all, where do these meet? We got to find where they cross. That way we know where to start and where to end. We need to know our boundaries of integration. Okay, so first of all, before we do any calculus, let's just go ahead and figure out where these meet. X to the 3 halves. We're going to try to find where they cross, the intersections of x to the 3 halves. And the way we find the intersections of our graphs is we simply take the equations of our graphs and set them equal to each other. Just like this. And now we could solve this. I could subtract the 2x over this way. So this could become x to the 3 halves equals to, minus 2x is equal to 0. I notice a common factor of x, which I can now pull out. So that'll give me x times x to the 1 half minus 2 is equal to 0. And now each of those is nice to solve. If x equals to 0, well, then x equals to 0. All right, awesome. If x to the 1 half minus 2 is equal to 0, well, let's see. X to the 1 half minus 2 equals to 0. Add the 2 to the other side. And now I can square both sides. And that'll isolate my x. So here x must equal to 4. All right, so we know our boundaries. Notice that our boundaries here are with respect to x, which means we want to treat this as a vertically simple region. When your x's are constants, you can treat that as a vertically simple region. So not only does this tell us where our boundaries are, it tells us which region we're trying to use. All right, so let's go ahead and do that. The area of our region is going to be given by the iterated integral. We're going to take our constant boundaries, and we're going to treat those as the outer boundaries of our outer integral. We're going to take our actual functions here, and we're going to treat them as the inner boundaries of our integral. So we want the upper one first, which is going to be the linear equation. It's going to be 2x, and we want the lower one, which is going to be x to the 3 halves. You might say, how did you know those? You can always just plug in a number. We know we want this region we want this to exist between 0 and 4. So just pick a number halfway in between 0 and 4. I could use 2, or I could use 1 or 3 or whatever. So let me just use the number 1, in fact. If I plug in the number 1 here, that's 1. If I plug in the number 1 here, that's 2. Oh, that means in this region, that's got to be higher. So that's going to be my upper bound. And since that would be lower, that's got to be my lower bound. All right, and then since it's a vertically simple region, this integration will be with respect to y first and then with respect to x. If you don't have this handy, this right here also tells you what to do. Hey, look, these are what y is equal to. So you're integrating with respect to y. This is what x is equal to. All right, that's what x is equal to. Okay, so then you'd integrate with respect to x, just like that. So now we can find this area. Take the inner integral first. Start with this integral with respect to y. Okay, so that's going to be the integral from 0 to 4 of the integral with respect to y of, well, just dy here. That's just going to be y. And we're evaluating that from x to the 3 halves on the bottom up to 2x on the top, like this, dx. Notice that here we can just take these and set this equal to this. Separately, we'll set this equal to this, and then we'll subtract. So this gives us the integral from 0 to 4 of 2x goes first minus x to the 3 halves goes second dx. And now we just have a regular integral with respect to x. All right, so let's go and finish that off. Here, that's going to be the antiderivative of 2x with respect to x is x squared. The antiderivative of x to the 3 halves with respect to x is going to be x to the 5 halves. But then, dividing by 5 halves, that's the same as multiplying by 2/5. And then, this all goes from 0 up to 4. All right, so now it's just a little arithmetic. We're going to plug in our 4. That's going to be 4 squared minus 2 times 4 to the 5 halves. Oop. Over 5. Just this one's over 5. Not that one. And then separately, I'm going to say minus. And I plug in 0 here. That's going to be 0 squared minus 2 times 0 to the 5 halves over 5. Just like that. And so that's going to be 0. So let's not worry about that anymore. 0 minus 0, that's just 0. This one here, 4 squared will be 16 minus 4 to the 5 halves. Oh, let's see, that's 32 times 2 more. That's 64. And that's over 5, just like that. That's gone. Let's not worry about that anymore. So now that's going to be, let's give these a common denominator. So I can write this as what? 80 minus 64. So 80 over 5 minus 64 over 5 would give me 16 over 5. And there we go. So this 16 over 5 is the area between these two lines. Right. So here, give this a try. So go ahead and use an iterated integral to find the area bound between these two curves. Go ahead and pause the video, and whenever you're ready, unpause and we'll go through it together. All right, so first of all, we need to figure out where these cross. Okay, well, the intersection of the graphs is going to be found by just setting the two equations equal to each other and then solving the equation. Here we can subtract 4 from each side. We could even add the x squared over to that other side. So this will give me x squared minus 2x. I know some people are tempted to divide by x on both sides. Don't do that. Because if you divide by x, this goes from being quadratic to being linear. But remember, this is a quadratic, which means you'll have two solutions. If it's linear, you'll only find one solution, which means you won't be able to find the two boundaries. So move that over and then factor. We have x times x minus 2, like that. And so our solutions must be x equals to 0 and x is equal to 2. All right, so we have a vertically simple region, and we can go ahead and set up our area as being the integral. Here, we know these are constants, so our outermost integral will be with respect to x, and then our innermost integral will involve these two functions, the lower to the higher. Now again, which one's higher? Well, we can always just substitute in a number and see what happens. Right here, I'll just pick a number between 0 and 2. I'll pick 1. Here, 4 minus 1 is 3. Here, 4 minus 2 is 2. Oh, so that one's going to be higher. Okay, so here that one's going to be 4 minus x squared. That's my upper boundary. And this one's lower, so that's got to be my lower boundary. It's nice if you can graph these. But if you can't, it doesn't really make a difference. Notice we can still set this up without a problem. And now we can integrate. That first integral is nice and simple because, of course, it is a vertically simple region. And so we have just this integral. Well, the integral of dy is just going to be y. And that's evaluated from 4 minus 2x up to 4 minus x squared dx. We can now evaluate at these two by plugging this one in here, separately plugging this one in here, and then subtracting. So that'll give me the integral from 0 to 2 of 4 minus x squared minus 4 minus 2x dx. Here I can simplify that out a bit. That's the integral from 0 to 2 of, well, 4 minus 4 is 0, so that's gone. This will give me minus x Oh, sorry, that should be minus x squared. And here minus a minus will make that plus 2x. Just like that. And now we can go ahead and integrate that because that's just a nice polynomial function and we're looking for its definite integral. All right, so let's go ahead and do that. If we integrate this one, we're going to end up with negative x to the third over 3 plus x squared over 2. Oh, no, that's got a 2 there, so that 2 is not necessary, right? That 2 would divide out that 2. And then we're evaluating from 0 up to 2. All right, well, that'll be nice. We're just going to plug in these numbers. That'll give me negative of 2 to the third over 3 plus 2 squared minus, here if I plug in 0, I'm going to get minus 0 to the third over 3 plus 0 squared. Notice that's all 0, so we don't worry about that anymore. So this is going to be, that's just minus 0. That's going to be 2 to the third, that's 8 over 3. So I have negative 8 thirds plus 2 squared is 4. And if I take 4, which is the same as 12 thirds, minus 8 thirds, I get 4 thirds. Minus 0, well, that's still 4 thirds. So there we go. The area bound between those regions is 4 thirds. Now, you might be wondering, why are we doing it this way? Why are we finding an area using an iterated integral? I mean, these are perfectly well suited to do what we did in Cal 1. And that's to say, take the higher curve minus the lower curve and integrate from left to right. Why do we have to define it this way? Because in a moment, well, I suppose in a few sections, we're going to take this one step higher, dimensionally speaking. We're going to start looking at this in 3 dimensions. Here, this is still nice, and this still looks just like what we did back in Cal 1 because everything's still on the plane. But in just a bit, we're going to take this one step higher, dimensionally speaking, and then this won't evaluate quite as nicely as what we have here. So the reason we're doing this now is to get used to the technique, to get used to the computation, so that in the next sections, we're more adept at using it. Now, there is one last thing to consider when we're doing these kinds of computations. And that is, what if I can't take that integral? I mean, we've seen plenty of times in Cal 1 and Cal 2 where differentiation is relatively simple. Yeah, it might be long and cumbersome, but you can do it. If you stick at a derivative long enough, you'll eventually find it. An integral is much harder. And now I have an integral within an integral. So what happens if I can't find it? Well, surprisingly, in many cases, the fact that you have 2 integrals allows you to simplify things just a bit by choosing which integral goes first. Now you say, well, how do I choose which integral goes first? I thought it was already expressed. If your integral is with respect to y, then with respect to x, you don't have a choice. You integrate with respect to y first, and then with respect to x. Well, it turns out we have a little bit of flexibility, as we'll see here. So consider, and here we're going to talk about changing the order of integration. It's going to turn out that one of the reasons why integration was very difficult before is no longer the case. Now, that's just one of the reasons, right? There's still going to be plenty of times where integration's not very nice. But one of the things that we saw in previous courses, which made integration difficult, is now we can work around it. So let's consider this example. Let's try the integral from 0 to 2 of the integral from x to 2 of e to the minus y squared dy dx. Okay, and as always, we begin with this integration here. Okay, great. So all I need to do is to integrate e to the minus y squared with respect to y. And I don't really know how. Well, actually, I take that back. I kind of know how. If you think back to Calculus 2, we had a technique that involved a Taylor series. If you expand the Taylor series, or rather, if you expand this into its Taylor series, you can integrate the terms of the Taylor series one at a time. That gives you an infinite series. Can that be done? Sure. Oh, then can I evaluate at my endpoints? I think so, assuming everything converges. And then can I express that nicely? Depends what you mean by nicely. Oh, but then you're going to take that result and integrate again. Oh, that's not going to be good. So here, the only way that I know of, up to now, to integrate this right here on its own is not very nice at all. Well, it turns out that because we have a second integral, we have a little bit of wiggle room. We have a little bit of flexibility to make this problem a little simpler. Because notice what these are saying. These are saying that my is being integrated over a region that is simple in the x direction. What do you mean? Well, here, let's draw it. All right, let me draw this region. Forget about this integrand, just the region that's described by these boundaries. All right? So now, I know that x is bound between 0 and 2. Okay, so here's x is equal to 0, and here's x is equal to 2. So whatever I have is bound between those two. Here's x equals to 0, and here's x equals to 2. And I know that because x is equal to those two boundaries. All right, so now, if I have y is equal to x and y is equal to 2, well, I can graph those as well. Y is equal to x is a linear equation, but it's a really nice, simple linear equation, yeah? It's this right here. It's just y equals to x. So here's y equals to x. Right? And I have one more boundary. I have y is equal to 2. Oh, that's a constant. Y is equal to 2 is a flat line. And in fact, this is the point 2 comma 2. Because after all, if x is 2 here and x is equal to y, that means y is 2 right here. So this is a line that passes right through that point. All three of those meet at the same point, which is nice. That doesn't necessarily have to happen. We'll see in later sections where sometimes this is has to be broken up into 2 or 3 pieces. But for now, we're starting off with things nice and pretty. So the area that we're describing with these boundaries of integration is the stuff that's to the right of 0, but to the left of 2. Okay, so in between here and here. That's above x, but below 2. Okay, so that's my region. This is R. To the left of to the right of 0, to the left of 2. Between here and here. Above y equals x, but below y equals to 2. So that's all this stuff in here. That's my region. Well, now, this integration is difficult. I integrate with respect to y. Well, maybe if I just hold off on that. This is going to be one of the few times where procrastination is the correct answer. Here, I eventually have to integrate with respect to y. But maybe I don't have to do that right away. Maybe if I integrate with respect to x first, it'll change my problem enough that my integration with respect to y will be a little bit easier. So here, that's going to require me to change my boundaries of integration. Now you say, okay, so then just put the integrals like this. Put the x and the 2 out here, the 0 and the 2 in here. Well, unfortunately, we can't do that. Because if I put x and 2 out here, and 0 and 2 in here, notice these are not constants. And whenever you're dealing with a region, an integration to find an area, or to find a, let me not get ahead of myself, but whenever you're finding these integrations, you're supposed to have the outer bounds are constant. No matter which orientation your region has, your expression should have constant boundaries in its outermost integral. And here that wouldn't. That would not have a constant. So this is not valid. Okay, so what do? Let's re-describe our region. Because here, I don't want to describe my region with respect to y and then with respect to x. I want to do it the other way. I want to do it with respect to x and then with respect to y. So I switch those boundaries. And so now let's see. That's Well, let's start with this innermost function, with innermost integral. Okay, so now I'm integrating with respect to x, which means I want to describe x. I want to describe how far left and right I go. And you say, well, that's from 0 to 2. Well, no. Now I'm allowed to use variables here. Before I couldn't use variables. The outermost integration has to have constant boundaries. But now I'm allowed to use variables. And in fact, I'm going to have to. Because notice, if I'm going from left to right, okay, the left is always at the same spot. The left is always at 0. But notice, the right of this region varies. Right? Here, x is equal to 0. That's my lowermost boundary. But x doesn't always go up to 2. Sometimes it goes only a little bit. Sometimes it goes further. Sometimes it goes all the way to 2. Oh, well, notice it's going up to this line right here. So the furthest to the right x ever gets is x equals to y. Okay, so how far does x get? It gets as far as y. Notice these are constants with respect to x. I wouldn't put x here because that's not a constant with respect to x. These have to be constants with respect to this one. Okay, well, now that I've described the left and right, I need to describe the top and the bottom. But now, since that's the outermost set of boundaries, I have to do that with just constants. So here, the lowest constant, well, that's 0. And the highest constant, well, that's 2. So from 0 up to 2. This won't change. Whenever you change boundaries of integration, it'll change the order of integration. It'll change the boundaries of integration. The integrand itself doesn't change. That's just e to the minus y squared again. But notice now this integral can be done because now we're integrating with respect to x first. And now this is a constant with respect to x. And the integral of a constant is the constant times x. So this first integration is simple to pull off now. This is now e to the minus y squared times x, evaluated from wherever x is equal to 0 up to wherever x is equal to y. I still leave that integral there. I haven't done anything with that yet. And now I'm substituting in x is equal to y and x is equal to 0. Here, let me do that off to the side. Here, if I say x is equal to y, that's going to give me e to the minus y squared y. Minus, if I substitute in 0 for x, that's going to give me e to the minus y squared times 0. And since that's equal to 0, this goes away, and we're just left with e to the minus y squared times y. And I'll write the y in the front there. So this becomes the integral from 0 to 2. This whole thing inside is now this expression. It's now y e to the minus y squared. And now that's being integrated with respect to y. Notice this is now doable. I could just use a u substitution for this. So here, I can use a u substitution. Let's say I want the integral of y e to the minus y squared dy. I can take this power and call it u. U is equal to minus y squared. That means du is equal to minus 2y dy. And here, if I just divide both sides by negative 2, that's going to give me y dy. So this becomes the integral. That y dy is negative 1/2 du. This e to the minus y squared is really e to the u. And the integral of e to the u is just e to the u again. I would say plus a constant, but again, we're dealing with definite integrals, so that constant won't really be necessary for us. If we switch that back in terms of y, that's going to be minus 1/2 e to the minus y squared. It's just integration by substitution. So now over here, this is negative 1/2 e to the minus y squared, evaluated from where y is equal to 0 up to where y is equal to 2. Notice before we integrated with respect to x, so we set x equals to things. Now we integrate with respect to y, so we're setting y equal to things. And now we're just about done. We just need a little arithmetic here. We can substitute in the number 2 here. So it's going to be minus a half e to the minus 2 squared minus, that's going to be negative a half e to the minus 0 squared. For once, plugging in 0 doesn't make that 0. All right? After all, 0 squared is still 0, but e to the 0 is 1. So that's 1 times a negative a half. So that's negative a half. Here, that's e to the minus 4 times negative a half. So negative 1 half e to the minus 4. And here, double negative makes that a plus. So here I can write this as 1 half minus 1 half e to the minus 4. And I'm sure there's other ways we could simplify. We could put this down here, give them common denominators, factor out the 1 half. There's plenty of other things I'm sure we could do, but we won't. This will suffice. That's a perfectly acceptable answer. So you see that we are not necessarily stuck to the order of integration as it's written. We can change them if necessary, and sometimes it will be necessary to simplify our integrand to the point where it can be computed. All right, and so that is it for our section 4.1. For your homework, from section 4.1, oh, sorry, 14.1. Wow, I'm really far back, aren't I? 14.1, go ahead and try 3 through 49, every other odd. And then go ahead and try 61 through 67, and go ahead and do the odd ones for those. All right. So if you have any questions, please let me know, and I hope you all have a nice day.